Let's get started. So a couple of things. I forgot to get this out last time, but the homework 0 solutions are here. Pick one up on your way out. Homework 0, sorry. 0 homework 1. So I'm seeing interesting activity on the Kaggle page. As usual, there's me. John, somebody's beating that. So far, so good. Maybe one of you is beating the TA. Is Chetan here?
He's not here.
He's not here. I see a few people. I see a few people tied at 71025, which means they're all probably doing the same thing. Are any of these people here? You want to say briefly what you're doing, or you feel it'll let go of your position?
I have to remember what I did because I tried a couple different things. A lot of what I did was just computed the distance matrix and then just found the minimum. The sort of, I think it was, I tried like a variety of k values and then sort of found the minimum error based on k values.
Is that kind of what you're doing?
Yeah, I'm just doing squared Euclidean with like 10 years neighbors.
Okay, so you can get 71 with that configuration. Some people make slightly better, maybe a different K. Let's discuss this after the thing is over, so we'll know how to do it. Okay. Somebody asked a question on Scholar. I hope it's clear that this is your only evaluation for the Kaggle part. This is not test data. Right? The thing that you're uploading in your solutions is a plot of training error and cross-validation error. Okay? That's for you to realize which one of them you should look at for picking K. One of them, how is the behavior of both? Okay? All right, so that's that. And remember the project proposals. All right. So let's look at what we were talking about last time. So last time we went through sort of recap of where we are. So we looked at what we're implementing in the homework is a procedural view. There's a training stage and a testing stage, and we talked about how where we'd like to move is a statistical estimation view of things. So we'd like to view these samples as IID from some distributions, and we'd like to learn something about their distribution. And that's why we need sort of estimation theory is where we're going. We talked about different interpretations of probabilities, and this will play up again today because we're going to look at a frequentist estimator and a Bayesian estimator, and they will come back to this particular distinction about whether or not you view a variable as with the frequentist view probability of the Bayesian. Okay. We talked about marginals, conditionals, Bayes' rule. Just to jog your memory, we will see again concepts today of likelihood, prior, and posterior, and they're going to be extremely important. The thing that we will also make a connection today, why have we been bringing up KL divergence and why have we been manipulating homework 0? It's because you will see today that a particular estimator can be viewed as minimizing KL divergence. Okay? And that's what we'll see today. So the plan today is look at a toy problem, but go through maximum likelihood estimation, maximum posteriority estimation, and Bayesian estimation if we have time for that today. But we'll sort of go through a whole range of estimators for essentially a toy problem, but those same ideas will apply when it's no longer a toy. Okay? All right. Any questions about last time or the homework or anything? Okay. All right. So here's your first probabilistic learning algorithm. Here's the scenario. So after taking this class, you drop out of Virginia Tech and you join an illegal betting company. You feel that your skills are better utilized at making money, the most important thing in the world, rather than actually contributing to something. Fair enough. We actually will teach you ethics. All right. So your new boss asks you if Novak Djokovic and Rafael Nadal play tomorrow, will Nadal win or lose? Okay. And what is your answer? No, that is not your answer. Your answer is show me the data. Don't make a decision till you see data. Okay. So your answer is all right, show me the data. What happened in the past? And here's what happened. Nadal winning or losing, that's what WRL means. Nadal won, then lost, then won 2 matches. And so you say the probability that Nadal wins tomorrow is? What was that?
Is 2 consecutive recent one?
That's the entire thing. That's all of it. I don't know if there's any time aspect to this or not. Come on, guesses? 3 by 5. Okay. Why 3 by 5?
Because out of 5 times we won 3.
I'm sorry? Out of the data set that you gave me, there were 3 wins, 2 losses. I just normalized 3 by 5 felt like a probability. It was between 0 and 1, so there. So the number that came out was 3 by 5. I will claim that in your head you went through this entire picture. There is some unknown reality. There is a data set which are samples from a distribution. You formed a hypothesis class. There was an estimation algorithm that you used, and it gave out a number which is 3 by 5. And that's what we'll derive today. And this is vanilla estimation, but I'll claim that that's what happened. Okay, so let's do that. So like all other problems that we will face, there is some physical phenomena that we're trying to model. That physical phenomena in this case is Nadal winning, Nadal wins, Nadal loses. Right? Those are the 2 outcomes you're interested in, and you will try to form a model out of that. The obvious sort of modeling, this is reality of the physical phenomena. And you view this, and obviously in your head what starts is, all right, this is a random variable, right? So there are 2 states that can take, 0 and 1. I've studied that. That I know is pretty obvious. This could be losses or wins. This could be tails or heads. Any isomorphic labeling of that thing, right? But it's a binary random variable. And we know the perfect model for binary random variables. What is the model for binary random variables? Bernoulli. So here's your model, right? Is there a singular or a double? Dual. I'm getting half and half probability. Single L and a double L. Okay. So it's Bernoulli with some parameter theta, and this right here is your model or your hypothesis class. This was where the assumption was made that there is a space of possibilities denoted by this value theta. Right? So if I think of, here's all possible theta, I can view this on the number line between 0 and 1. I can also view it as a set. There is some reality which is theta star. It's the true value of Nadal winning, or that's what generates this, right? And that maybe on the number line as well. And in this case, this circle or this interval, that's your hypothesis class. Right? That's all possible models that you can encounter. In this case, you just happen to be lucky. The problem is, restricted enough, toyish enough that reality lies inside the model class. Often, for sophisticated phenomena, what will happen is, your model will say it's Bernoulli or it's binomial or it's something, and reality will not even be part of that model class. And what we'll have to do is search for the best thing in our model class. Okay? So the learning or estimation problem here is, we have committed to a model class which is Bernoulli. The estimation problem is find me a theta. Okay? So what's a good theta? How do we find a good theta? So in some sense, one way of finding a good theta is to ask the question, we are given a data set, right? That data set says, let's say, what did I have? 1, 0, 0, 1, 1, is that what I have on the slide? Okay. So there's a data set. What I can ask is, I need a particular theta that sort of, how do I find a theta given this data set? The question that you can ask yourself is, are there some theta values that make this data set most likely, that explain this data set? For example, why is this a bad estimator? Here's my estimator of theta, it's 0. The probability of Nadal winning is 0. Why is that a bad estimator?
He has already won.
I'm sorry?
Because he has already won.
Because in past he has already won. That can't possibly be right. It doesn't if this was true, I would never see this data point. Right? And therefore, this is also a bad estimator. Right? In fact, what you're essentially doing is you're trying to search for a parameter that explains this has already happened, right? The data set is in front of us that explains this data set. Right? This intuition is exactly the intuition captured by maximum likelihood estimation, which says, let's find the probability of this data set under our model for a parameter theta, and let's maximize that. Max theta, and this is your theta hat, and then maximum likelihood estimation. This function right here, we said, is the likelihood. Okay? So far with me?
Yeah.
It's going to get tricky. Likelihood functions are going to get tricky very quickly. What I want you to remember is likelihood is a function of the parameter, the theta. It is not a function of the data set, although it does change with the data set, but the way to think of it is we are changing the parameter. The notation that we'll often use is this, or this. So we're trying to say, the data set does matter, but we're essentially viewing it as a function of the parameter. Okay? And often when the data set is not changing, we will not have any explicit dependence on the data set. We'll just write it as L of theta. What does it look like? Here's what it looks like. So if I give you a data set which is extremely toy, it just consists of one sample, heads came up or Nadal won, the probability of the data set, remember, is the product probability of y equals little y theta I equals 1 to n. It factorizes for each random variable. Why does it factorize? Why can I write it as a product? ID assumption, exactly. So we've made an assumption that the data set, which consists of y1, y2, y3, yn, are essentially independent, identically distributed random variables, so I can multiply these things. Okay? So I just have to multiply probability. It doesn't show up in this case, there's only one random variable. The likelihood function here is the probability of y equals 1 given theta. So this is just the function. This is just the function theta. Here's what this looks like if I try to draw this. There's 0, there's 1. This is likelihood of theta. Okay? I've drawn, likelihood is a confusing concept often because you start thinking of likelihood as probabilities. And it feels like, oh, it's a probability, it must sum to 1 somehow. It's not going to sum to 1 in the variable that we're plotting it in. Right? It's clear that this is not going to integrate to 1. This is a continuous function, it's not going to integrate to 1. This is essentially a triangle, half 1 times 1, the area is half, it's not going to be 1. Right? And it's because that's not the variable under which it's a distribution. It's the data set. If you summed over all possible data sets, then you'd get to 1. But this is a function. Right? And it's clear that if this was the likelihood function, and the estimator was maximum likelihood, it's just an increasing function, right? It says, oh, there, pick this point. Which makes sense. Emily is saying, I observed 1 win, Nadal's going to win every time. Right? Here's another data set, 1 and 0. The likelihood function is probability of y equals 1 given theta times probability of y equals 0 given theta. independent. We'll just write that theta times 1 minus theta. This function looks slightly different. Actually looks like an inverted parabola. Achieves the maximum at half. And if you solve this, it's going to say, theta hat, where it achieves this function, achieves the maximum at half. Make sense? And if your data set was, let's say 1, 1, 1, your likelihood function would have been theta cubed. Right? So this function would have looked kind of like this. 1 versus theta. Does that make sense? Yes?
The likelihood function, what does it physically represent?
So it's physically trying to represent the world already happened. This data set happened. You collected some data, you came back. The likelihood function is trying to say, in your model class, if as I drew a set or an interval, like on the right hand side, all the curves are for an interval because there's only one parameter. But there may be many parameters in your model class. So you try every single possible parameter and you check, does this make the data set that you just collected likely? Right? Does this explain your data? Does that make sense? So this, for example, can be symptoms that a patient comes with, and this can be the possible diseases. Right? I try different diseases. Does that explain the symptoms? And I should go with the disease that explains the symptoms the most. Does that make sense? In this case, the model is just a coin toss, right? So there's only one parameter and can go between 0 to 1. Any questions? Okay. So far so good. A couple of examples. Obviously, in the general case, this is my favorite kind of proof by ellipsis again. Turns out to be theta to the alpha heads 1 minus theta to the alpha tails, where alpha heads is just the number of heads or wins or ones, and alpha tails is the number of tails or losses or zeros. Right. Just count how many times that's happening. That's the probability of that happening is theta, they get multiplied. The probability of other thing happening is 1 minus theta, they get multiplied that many times, and so you get this. That makes sense? All right, so this is a function. It's some sort of a polynomial function between 0 and 1. You want to maximize it, find out, in theta cube it looks like this, theta times 1 minus theta it looks like this, theta it looks like this, and we want to find where does this function peak. Right? Should be seems pretty straightforward. So this is going to be a fairly standard trick that you're going to often use in some of these derivations. Anytime you're faced with these sort of complicated polynomial-looking functions, the things that you're going to do are theta hat MLE is equal to argmax of theta of likelihood of theta, and this is also equal to argmax of theta of log likelihood of theta. Why is this true?
Log is a monotonic increasing.
Log is a monotonic function, doesn't change the argmax. If the log looks like this, as the value inside, as the likelihood increases, so does log, and therefore whatever maximizes the output of this monotonic function also maximizes that. Its argmax doesn't change. Great, the math becomes a lot easier. The first order calculus becomes a lot easier. This is just alpha heads log theta plus alpha tails log 1 minus theta And we know how to do this, right? This is first order methods. Take the derivative, set it equal to 0, and what you'll get is alpha heads by theta plus alpha tails minus alpha tails 1 minus theta equals 0. I'm making an assumption in here that alpha is neither 0 nor 1, otherwise the derivatives would be defined. Okay, those are boundary conditions. I'm assuming that theta is not equal to 1 and it's not equal to 0. You can check that pretty easily on your data set, right? Because if everything that you've seen so far is ones, then you know how to check those boundary conditions. Yes?
What if like, so if the dimensions of theta is like 3 or like multiple, then what happens?
Then it doesn't become one parameter, then it's a whole set of derivatives, partial derivatives with respect to a whole bunch of variables. You don't get one equation, you get a system of equations. You have to set them equal to 0 and solve for all.
And what does theta hat represent? Like what input?
Sorry, I put a hat anytime I'm estimating a value. Right? So theta hat MLE is my estimated value of theta. So I've just set the first derivative equal to 0, and that gives me the standard result. Theta hat MLE equals alpha heads by alpha heads plus alpha tails. That makes sense? Just cross multiply, set it equal to 0, you'll get, so that's the estimate.
Alpha head and alpha tail, the probabilities of the,
No,
likelihoods.
not the probabilities, not the likelihoods. Alpha heads is just the number of times you have observed heads in data set. So just go ahead and count the number of heads. Okay. So if that was your data set, alpha heads is 3, alpha tails is 1 for that data set. Okay. So 3 plus 2, 3.5, not bad. You got the answer that you wanted. So, you went through a couple of steps. You derived the model class, wrote down the likelihood, took the first derivative, differentiated, set it equals 0, got an estimator, set the values. You guys are pretty quick. All of that in a few seconds. Okay. Any questions about MLE so far? Okay, so what's a good theta? The ones that makes it likely for us to have seen this. Let me come back to this. Okay, so that's the maximum likelihood estimation. Things will change, the meaning of random variables will change, the model will not be a Bernoulli, the model will be something else, but there will always be a data set, some parameters that you want to estimate, some likelihood function that you would write down, maximize. Right? It's always going to be, write down the likelihood function, crank out your first order calculus. Not much after. Okay, but why maximum likelihood? Why is this a good thing to do? Any guesses? I mean, I made a hand-wavy argument. It explains the data. It sort of feels nice. Yes?
You can use it with Bayes theorem.
You can use it with Bayes theorem, but we didn't say anything about the Bayes theorem so far. No Bayes rule. Yes?
I was gonna say, if you wanna like recreate the data you saw, like that model would be like really good. Like it'll just reduce that same data.
Yeah, so if I saw a particular pattern of wins and losses, after I find this parameter and I start sampling more data from my model, it will look like it's coming from the original data. Yeah, that's one intuition. Yes?
For the prediction, we can learn from data to certain parameters in an optimal way, so the prediction use for the posterior probability use this data value.
There are no posteriors right now. Didn't talk about priors, no posteriors. We're in the land of frequentist statistics.
It's the most likely. It's the most likely model.
Well, that's in the name, yes. It is the most likely. But you could also define likelihood as how many times can you jump, and then that would also be most likely. But why is likelihood, the probability of the data given? the parameter.
Unless something bad had happened, I mean, your data set in the future is going to be the same as the data set that you saw in the past.
Yeah. So these intuitions are all correct. It is, you're fitting. The intuition that you should keep in mind is there's a large model class. There is a lot of, theta can be anywhere from 0 to 1. The event that you're interested in can never happen, it can always happen, or anything in between. And what you're doing is you're trying to find where in your model class is something that generates data or produces data that matches what I've already seen, or that explains this data set that I've already seen. That makes sense? Often it's going to lead to extremely natural estimators. When you crank out the math, we'll be sort of surprised with the estimator that it tells us to do. Right? The estimator it told us was just count the number of heads and divide by the total number of samples. Extremely natural thing to do. That is what we would have done had we not known about any of this theory. Right? And this is going to happen a lot with MLE estimator. It's going to feel extremely natural, the estimators. And here's another sort of really nice result that will do a little bit of that derivation now. MLE, it's going to be a strong claim. The claim is MLE is going to be the optimal thing to do, and I'll define optimal in a second. There's a star up there, and there are some conditions, but it is the optimal thing to do if your model class is correct. So it is the optimal thing to do if you know where the data is coming from, what model class. You don't know what data is, for example. You don't know that particular parameter, but you know it is a coin toss problem. If you know that the model class is Bernoulli, when you do an MLE, you will get the right answer. All right, let's work through that. So, any questions about the statement of that claim?
If you don't know then how can you even have the likelihood function?
Wait. So you can always assume that a particular model class, right? It could be the case that there's 10,000 possibilities for a particular random variable, but I only treat it as a 0-1 problem, right? In which case my model class is just incorrect. It's not capturing reality. All right, so here's what we're going to try to prove. So what I'm going to consider is, let's say y is your random variable, and let's say it's discrete. Right? So I'm going to make things simple, and I'm going to assume it's discrete, but the argument will generalize to other kinds of models. This will make just the math easier for me. And the thing that I'll consider, that I'll think about, is log likelihood for some model, and average divided by the data points. And so this is what that looks like, right? It's summed over I going from 1 through n, just 1 over n. Right? What I'm supposed to do is I'm supposed to take the log probability of the ith sample divided by given theta. Okay? So far, just the definition of the log likelihood. Okay? And what I'm going to claim, so this is a summation. Right? This goes from 1 through n. You have n data points, and all you're doing is you go to the data point, you ask it. Let's say this is a die, right? This is this goes from, it's a discrete random value, goes to 1 through k. You check the first data point, comes out 2. All right, what is the probability of 2 given this parameter? Second data point comes out 3. What's the probability of 3? I claim that I can count this summation another way. And here's how I can count this summation. I can first make a histogram of how many times did 1 happen, how many times did 2 happen, how many times did 3 happen, how many times did k happen. And then I can just directly multiply the probability of that happening. Right? So this is just a counting argument. So I can say how many times is y equals 1 times probability of y equals 1 given theta. Right? Plus, I can say how many times is y equals 2 times, sorry, I should get log here, log probability, times log probability of y equals 2 given that, and so on, all the way to k. Right? Is it clear that this is Just a different way of counting the same summation. So far with me? Yeah? Okay, this is just histogram. How many times is this happening? How many times is this happening? And just multiply it. All right, but now this is where a little bit of argument will come in. The number of times y is set to 1 divided by n as I see infinite data. What is that equal to? Probability. With probability of what? Probability of y equals 1. So far, so good. But probability of y equals 1 under the correct model. We don't know what theta star is. Under the true model, the model that generated this data, right? How, you're seeing some data set. How many times are you supposed to see 1? Well, depends on what the parameter was, right? So we don't know what this theta star is, but we know that as the data set becomes infinity, this becomes equal to that. Okay? And what I'm going to do is I'm going to use a shorthand. I'm going to call this term where probability of y equals 1, theta star. I'm just going to say this is p star of 1 or p star of y, right? Little y. This is the correct probability, the probability under the correct model. Okay. And the probability of y equals little y under some theta that you're considering, I'm going to call that p sub theta of y. Okay. They're both probabilities. One is under the true model, one is under the model that we are considering. Okay? And it should be very clear that there are those terms appearing here in the summation. N, if I take inside, and I take the limit as n goes to infinity, as we have infinite data, this becomes p star. Right? So this becomes p star of 1 log p theta of 1 plus all the way to p. Does that make sense? This term, the count of y equals 1 divided by n, becomes the true probability. How many times am I supposed to see 1? Times just this. How many times is how much probability is my model assigning to the state 1? Plus all the same. And I can write this as just a general summation over all possible states y equals 1 to k, p star of y log p theta of y. Make sense? All right, we're almost there. 2 steps and why am I doing this should make sense. Magically, I think I should multiply and divide by something. So I will multiply and divide by p theta of y inside the log. I'm assuming boundary conditions that this is not actually 0. If it was 0, then I don't have to consider it in the summation. So it's make life easy, right? So multiply and divide by that. All right. So this becomes summation over y, p star y log p star y minus summation over y, p star of y log p star of y divided by p theta of y. I just took this one term and put it here. The other two are sitting here, except in the flipped order. And I added a minus. All right. So far, a simple algebra. Just manipulating terms around. Can anybody tell me what these terms remind you of? What do they look like? Yeah, so the second is looking like a KL divergence term. This term right here is the KL divergence between P star and P theta. 2 distributions, one which is reality, that's the correct model, one that we're considering. Right? And what is this term right here? Entropy, or more specifically, negative entropy. But importantly of P star, not of P theta. So as you change theta, this is a constant. This doesn't depend on theta. Right? This is just how much entropy is in that distribution that generated your data set. Is Nadal always going to win? Or is it 50-50? Or is one of them always going to win, right? It doesn't matter what model class you choose. All right, so started with average log likelihood. Wrote it out as entropy plus scale divergence. I was asked to perform an argmax of this. Constant is equal to argmin of scale divergence. Very nice. So the reason why we're doing maximum likelihood estimation is because it's the closest distribution to the reality if we had infinite data. And if your model class is correct, then whatever theta star actually is achievable with this. And so you will get to a 0 KL divergence when you minimize this argument. Does that make sense? So if it is the case that this is your model class and theta star sits inside the model class, then when you minimize the scale divergence, your theta hat or your estimator will actually be this. However, if reality is outside your model class, you will find something that is closest. This is theta star, this will become theta hat, and then this will be closest in KL divergence. That makes sense? Okay. The reason why we did this is to show that, I made the assumption that it was discrete. That assumption doesn't need to hold. I actually never assumed anything about this true model. Right? It could be any true model, and this entire derivation will come through. So it's a really strong statement that it doesn't matter what model is correct, as long as your model class is large enough to contain reality, you will be able to find it with infinite data. Okay? So there were two caveats made there, two assumptions made there. One is this results only holds for infinite data, and the second thing is that you need to know what the model class is when your data is coming. If you don't, if there's a mismatch, then all bets are off. That make sense? Any questions? Yes?
I'm just having trouble understanding the very first line, so that the log, you're saying that the log likelihood is equal to that summation.
Yeah. So this is just the definition of log likelihood, right? This is the likelihood factorized, right? It was just the likelihood of theta. The likelihood of theta under IID assumption was just I equals 1 through n, probability of y equals little y, given theta. The ith sample, how likely am I to see the ith sample given my parameter? Right? And I'm just multiplying that because there's the IID assumption. If I take a log, then the multiplication becomes a summation. Okay? So that's why that's just log likelihood, and this is just average log likelihood.
And I guess the one over n is kind of confusing. Like you're averaging. I don't know.
You're averaging. So this is a number between 0 and 1. This is a number. Log probability is a number between negative infinity to 0.
Yeah.
I'm just averaging that number. That tells me on average across my data set how well is my model explaining. The average is important because otherwise if you have a larger data set, you just get smaller and smaller numbers, right? There's a negative numbers, just keep adding them. And so that's why it's important to sort of make comparable statements.
Okay, thank you.
I have one question. Did we just prove that the problem of finding a theta that maximizes your log likelihood is same as finding theta that minimizes your KL divergence?
Yeah.
But in order to minimize the KL divergence, in order to find the KL divergence, we need two probability distribution or two models. One is the actual one.
Yeah.
Another one is the what you assumed.
Yeah.
So, but we assumed the actual one to be our assumed one. So
No. We didn't assume the actual one to be our model. What we assumed was when you have infinite data, the relative frequencies of the various states of this discrete random variable essentially converge to the true distribution. Right? There was an argument, this argument, that I only see samples, but if I count my samples and I actually see infinite data, then that is converging to this number. So I don't know what theta star is, but with enough data, I have a good handle on what these probabilities are. Does that make sense? Let me finish that question. Does that make sense?
So like don't we need both p theta y and p star y? So
yeah, we have both of them, right? So this ratio of number of samples divided by n converges to p star of y. That's right here. And I just followed that through, and it became here divergence between p star to p theta. Right? And in practice, I don't need to minimize the scale divergence. Right? In practice, I don't know what p star is. In practice, I'm going to actually just do argmax of this thing. Right? And as I have more data sets, that's just going to converge to the right quantity. Okay, let's take a minute. It represents the Thank you. It's something that dolls are some probability. I don't know what that is. All I see is the past. I'd like to find what that theta star is. That's what I'm trying to do with this the theta star is a constant. Theta star is unknown. I don't know what theta star is. Whatever it is, it does not change when I change my model. Whatever, think of it as a patient and the patient already exists, he has some symptoms. The doctor all right. Okay, so I want to take this, let's see, okay. So I want to come back. So now we know MLE is a good thing to do in the Bernoulli model case. It leads to this estimator which says just count the number of heads divided by the number of heads plus tails. I want to use this to just explain the concept of what a sufficient statistic is. You're going to do this a lot. In fact, you've already interacted with sufficient statistics in Homework 0. We just didn't call it a sufficient statistic. It's this idea that if I give you two different data sets, for example, here's win-win-win, lose-lose-lose, and here's an alternation of that, what is the estimated parameter for both those data sets? It's the same. The reason why it's the same is because the number of heads and the number of tails are identical in these two data sets. So these are two different data sets that look alike or lead to the same estimation of your parameter. It's not just that the argmax of the likelihood function is the same, it's that the likelihood function is identical. Right? And we're going to use this sort of a definition that there is a function of the data phi of x will be called a sufficient statistic if whenever the sum of the sufficient statistic is identical between two data sets, right? So in that case, the sufficient statistic can be are you heads or not, right? Is xi equals 1 or is yi equals 1? If that's the function, when you sum it up over d1 and d2, if those are identical, which means the alpha heads is the same as alpha heads in this data set is the same as alpha head in this data set, and by the fact that there's only heads or tails, the other ones also have to be the same. This is going to lead to the likelihood functions being identical. because theta to the power of alpha heads 1 minus theta to the power of alpha tails, right? So whenever this will hold, we're going to call this your sufficient statistic. This is all I need to know about the data set in order for me to perform the likelihood-based computation. Does that make sense? And in fact, what you did in homework 0 was to compute x and x squared in the online question, right? You have to do one stream pass of x and x squared. And those are sufficient statistics under the Gaussian distribution. If you know what those are, then you can then the likelihood functions under the Gaussian series.
So does it mean that if the data sets, the two data sets have the same pattern, then the likelihood is going to be the same?
By pattern, if you mean this particular function, then yes. These are two different data sets, right? In this case, they are just permutations of each other, but that may not always be the case. It depends on how you're defining this function. Right? This function for the coin toss case is just, it's a binary function that says, is xi equals 1? Right? And if you sum that up on the left, on one data set and another data set, they end up being identical, and all the likelihoods are the same. But for other distributions, for example, the Gaussian distributions, we haven't talked about it. For a Gaussian distribution, this thing is a vector of x and xi squared. And if they sum up to the same thing, then the likelihood functions are going to be essentially identical. Okay? So any inferences that you make from a data set are going to be identical if they're sufficient statistics. Yes?
You mentioned that the likelihood function will be same, but not necessarily the optimal theta.
No, I said not just the optimal, all the entire likelihood functions. It's not just that you have two different likelihood functions that peak at the same point. It's that the functions are identical. Okay, so this maximum likelihood is an example of frequentist estimation. And you'll know in a second why I'm saying that. So you come up with this estimator, number of heads by number of heads plus tails. Your boss says, remember we were counting for Nadal. Last year, 3 heads of wins for Nadal, 2 losses for Nadal. So your estimator is 3 over 5, and you confidently say, now I've gone through this entire derivation, I can actually prove this, or at least some semblance of the proof. I can regenerate it. What if your data set is 30 heads and 20 losses, 30 wins and 20 losses? The same. More data didn't help, and you can prove that as well. And so what's better? If I come to you with a data set that contains 3 wins, 2 losses, or a data set that contains 30 wins, 20 losses, which one's better? Second one. Why?
More data.
More data. We've been told more data is good. Your estimator doesn't reflect that. Your estimator essentially gives the same answer. Not essentially, exactly gives you the same answer. And so your answer is essentially more the merrier. No, yes.
You can see like the conversion.
There's no convergence result there, right? It's just a claim that says just count.
The estimator, we made that assumption that it is 2 under infinite data, so more and more data
yes.
we get,
So
we are approaching.
The more you get closer to infinity, but we didn't make any claim that as you get closer, you get lighter estimation. Yes, but those are the right intuition. So this was one angle, that your MLE estimator doesn't actually convey a sense of confidence based on how much data you're seeing. In fact, it's extremely susceptible. If I just give you one sample point, which is 1 win, you confidently return, we haven't talked about any sense of confidence, but your estimator just becomes Nadal is always going to win. Forever and ever, no matter when they play, the probability that Nadal will win as well. Right? So let's talk about another issue. That was one issue, and we'll address. The other issue may be, you may actually have prior beliefs. You may say, right, last year he lost, but I know in my heart of hearts he's a better player on clay courts. Why does your inference doesn't show that? Where can I put that in? And if you're willing to do that, then that's where Bayesian statistics come in. So the idea of Bayesian statistics is going to be that you're going to treat that unknown quantity theta, which is the parameter that you'd like to estimate, you would like to view it as a random variable. And that's going to be an important distinction. That's where it's going to branch off from frequentist statistics. In frequentist statistics, theta is an unknown, but it's constant. There is only one world, there is only one Nadal, there's only one Djokovic, and so there is only one parameter or probability that determines on average who's going to win. Right? Theta is not an unknown, is not a random quantity. But if you're a Bayesian, probabilities are just about your beliefs. And so you can put beliefs on any quantity that is true or false, right? Or any particular quantity. So let's talk about that. So in Bayesian analysis, the thing that we're going to talk about is the posterior. So what do I believe about this parameter after I have observed this data set? And simple Bayes rule is going to tell you that this is the likelihood times the prior divided by the difference, right? In frequentist statistics, you cannot talk about the probability of theta because theta is not a random variable. It is an unknown constant, but it is not a random variable, and it is not a repeating, recurring random variable, right? But in Bayesian statistics, we can talk about your confidence or your prior beliefs about theta. And so what we're going to need is some probability distribution or some density function between 0 and 1 that is going to tell us how much do you believe, at this time it's going to be P of theta, and this time this is going to integrate to 1. What do you believe about theta? Is it closer to 0? Is it closer to 1? Does that make sense? And what we're going to do is we're going to work with a particular estimator called theta MAP, maximum a posteriori, which is going to be argmax of the posterior distribution. Right? So after you have observed some data set, what do you believe about this? And that's going to be some density function. It's going to be some distribution between 0 and 1. And I'm going to ask you, what do you believe in the most? Right? The thing to immediately notice is if your density function is constant, right? If P of theta is a constant, what is this reduced to? It's theta at MLE. Because this quantity is constant with respect to theta. This quantity is now also constant with respect to theta. So the argmax is only happening because of this. Does that make sense? Okay. In our particular, let's see, this. So priors are going to be the probability of your parameters before you see any data set. They're going to basically help you express beliefs about. So this is where domain expertise is going to come in. If it is a medical, for example, application, you will ask doctors how likely is this disease just a priori, right? And if it's unlikely, then you're going to downweight even if the likelihood says that this disease perfectly explains these symptoms. Later on, we're going to view priors as essentially something called regularizers. They're going to shift your focus towards simpler models. They're going to prevent you from overfitting, and we're going to talk about that later. And there's also going to be computational ease. So a lot of times priors are going to be chosen essentially because it will make the math work out simpler, even if you're trying to get to MLE estimators. And in that sense, one concept that is going to be important is something called the conjugate priors, and you will see conjugate priors in the example that we're talking about. So in our running example, which is, I have a random variable, take 0, 1, it's Bernoulli, I I have a parameter theta, it's between 0 and 1. Here's a particular prior distribution. This is called the beta distribution. Looks complicated, looks messy. There is some, this is the, remember this is the density function. How, what is the probability of theta? It depends on two parameters or hyperparameters this time. These are called hyperparameters because they are parameters of the distribution on the parameter of something else. Okay? And there's a whole field of literature called hierarchical Bayes where you're going to put parameters on parameters, priors on priors and priors and priors. So here the parameter is playing a role in the exponent. Here's another parameter which is playing another role in the exponent. Here's what it's going to look like. So let me show you this. So remember it was theta to the beta heads, and it's going to be pretty clear in a second why I'm calling this beta heads and beta tails. Think of this as just two parameters that control the shape of this distribution. Interestingly, and this visualization calls them alpha and beta, but think of them as beta heads, beta tails. When they're both 1, it's a distribution that is constant. It's a uniform distribution between 0 and 1, right? That's why it's a flat line. So here's my two-dimensional parameter space. As I increase those two parameters, so beta heads is 2.24, beta tails is 2.2. What I'm sticking to right now is this diagonal line, right? So I'm sticking, they're both essentially equal. As long as they're equal, the mode of this distribution will be at 0.5. As you increase the magnitude of those two numbers, the distribution will get more and more peaky. So initially at 1 and 1, you don't believe anything. Anything could happen. It could be the case that the coin that you're tossing is completely biased with probability 1. It could be the case that the coin is completely unbiased the other end, probability 0, or anything in between. As you increase those two numbers, you're seeing this is a perfectly valid distribution on this continuous space. It just has a really high belief on the even, the 0.5 probability. Right? As the numbers are still equal, as I take them closer to 1 and 1, the distribution becomes flatter and flatter. At some point, when I cross over, when both become less than 1, then the peaks of the distribution lie at the extremes. At this point, you don't know which way the coin is biased, but you're pretty sure the coin is biased, right? It's a perfectly valid distribution, right? Integrates to 1, the coin could be biased either way. And you could sort of take this all the way to 0.01, 0.2. And obviously we can sort of stay in this regime where one number is high, the other number is small. This is beta tails, and so in this case you place very high belief that the coin was biased this way. Or I could be in this regime where beta heads is high, the other number is small. In this case, you have very high belief that a priori belief that the coin is biased this way. Does that make sense? And in this 2D space, every single point in this 2D space is a particular prior that you start with. This is what you believe about the coin before any tosses. That makes sense? And what you're going to do is you're going to multiply, there's a prior term here. You're going to multiply that prior with this likelihood. You observe some coin tosses, and that is going to construct the posterior that is written. That makes sense? Alright, so let's do that. It's going to not be too terribly difficult. So what did we say? We said we're interested in argmax. Argmax just depends on these two terms, so I'm going to just drop. I'm going to change this to a proportionality sign. It'll still work because the argmax are still the same. The likelihood term that we've been working with so far, it was theta to the alpha heads, 1 minus theta to the alpha tails. Right? That was just the likelihood. The prior was something ugly, but all I remember and care about is beta heads minus 1 minus theta raised to the beta tails minus 1 divided by some constant. I don't really care what that constant is. Okay. And the reason why we chose this prior, you'll notice, is exactly because things are going to multiply really easily, right? This is going to be theta to the alpha heads plus beta heads minus 1 minus theta to the alpha heads plus beta heads minus 1 divided by some uglier constants. Okay. What does that look like? Beta heads. Excellent. So don't have to worry about constants, don't have to integrate. We know exactly what this is. This is a beta distribution with particular parameters, this time alpha heads plus beta heads, alpha tails plus beta tails. That's the reason why we were working with this distribution. This is an example of a conjugate prior, when the prior multiplies with the likelihood to lead to the same family of distributions on the posterior. That's a conjugate prior.
We originally had for that constant b function with parameters beta heads and beta t, right?
Yeah.
So maybe I didn't see that. It's not exactly constant because it's a function of beta t and beta heads.
But those are just parameters, right? This is we're right now it's constant with respect to theta, right? So this is just like think of a Gaussian. X minus mu divided by sigma square. There's a 1 over root 2 pi sigma square centimeter. The 1 over root 2 pi is essentially constant, and you're only worrying about it. Okay. So this is actually one of the reasons why we worked with this distribution, because the posterior ended up being something nice.
The exponents here would be alpha tails and beta tails for 1 minus 1.
Oh, thank you. Alpha tails, beta tails, minus 1. Yes, thank you. Right, and the nice part about this is that this is again some function between 0 and 1, right? This is a beta distribution. It's some function between 0 and 1. And what the MAP estimator is asking you to do is to find the mode of this. And some mathematician at some point calculated that and gave us a closed form expression, right? So we don't have to worry about that. And so the mode of beta heads, beta tails. So the mode, beta hat mode lies at beta heads divided by beta heads plus beta tails minus 2. That's the mode of this distribution. We're interested in the mode of this distribution. And so theta hat MAP ends up being alpha heads. Let me write this here. This is important. So theta hat MAP is equal to alpha heads plus beta heads divided by alpha heads plus beta heads plus alpha tails plus beta tails minus 2. Oh, I made a mistake. There's a minus 1 here. Okay, why did we do this? Why did we torture ourselves? So this looks like an expression that almost looks like an MLE. Can we convert this into an MLE?
By putting one beta h and beta tails 1.
Put beta h and beta tails equal to 1. Excellent. And what happened to the prior distribution when you set them to 1?
Uniform distribution.
Uniform distribution. So the MAP estimator was converting into the MLE estimator when it chose parameters that made it into a uniform distribution. Right. The way to think of this, the reason why we've been calling them the beta heads and tails, the way to think of them is pseudo counts. These are counts that happened before your experiment started. If I made this number 10,000 and this number 1, the probability that you start off with, before you see any data, right, these are all 0. You start off with a very heavy bias, the coin is biased towards 1. And then it takes you a lot of data to overcome that bias. right? You have to keep seeing coins. No man, it's still zero. It's just still zero. It takes you like 10,000 flips before you can actually converge to a uniform distribution. So those are pseudo flips or pseudo counts that that your prior is already telling you. So there's a nice sort of intuitive interpretation between the parameters that control your prior and the estimator that results with the posterior. That makes sense?
So in our example, beta would be related to Nadal's battle on play, but alpha would be related to how many times Nadal has won in the past.
Yeah. So alpha would be related to how many times have I observed Nadal winning, and beta would be related to just what do you believe. If you believe strongly that Nadal should win on a clay court and Nadal is just inherently better, then you have a large beta heads and a smaller beta tails.
And those are the beta, are there counts or probabilities?
Beta are counts.
Okay.
They are counts. They don't have to be integers because they are just parameters that control another distribution. Right? And that's what I was showing in that sort of 2D plot.
Yeah.
Yes.
So finally we have a distribution for posterior, right?
Yes.
So it has two parameters. So yeah, when we are explaining about math, should we have two values for two parameters?
So these are parameters of a distribution, but the distribution is on theta. Right. So let me show the plot. This makes sense visually. So remember in this particular example that we've been working with, this illustration, on the x, in this case I'm confusingly alpha and beta, but it's actually beta heads and beta tails. This is the 2D plot of the parameters. As you vary the parameters, your distribution over theta, the shape changes, and what we're asking for is what is the theta at which this distribution reaches the highest point. Right? So the MAP or the mode is with respect to the x-axis, and the x-axis is theta, because it's a distribution of theta. This integrates to 1. The area under this curve is 1 with respect to theta. Right? Those two are fixed constants that determine the shape of this. That make sense? Any questions? Okay. Not bad, not bad. So, different settings of the parameter values you will start off with different priors. That will change the shape of the prior. The prior is going to multiply with the likelihood to lead to a posterior. It's a conjugate prior, so the posterior of theta, given the data set, things will nicely multiply. We won't have to worry about the constants. We already know what family it lies in. And therefore, since we know what family it lies in, we know where the mode lies, and so we can use it. And the beta prior is equivalent to extra matches that you start off with before the data sets. Okay? If you imagine our estimator behind this, the thing to remember is as you get infinite data, as n goes to infinity, your prior is forgotten. Alpha changes, but beta doesn't change. Right? It's alpha. I should just write it down. Alpha heads plus beta heads, alpha heads, beta heads plus. This is the estimator. As you see more matches, the alphas change, the betas are constants, right, that you start off with. So as you see infinite data, as n goes to infinity, this is a constant in the numerator, a constant in the denominator, they both vanish. The terms that dominate are these two terms. Right? So it converges to the MLE estimator with infinite data. That make sense? So your prior is forgotten as you see infinite data. So it makes sense, right? But for small sample sizes, the prior is going to be extremely important. So the thing to keep in mind is this picture, and I really, really like this picture. So here's the prior that you start off with. You believe that the coin is mostly, so this is probability of here's this, right? Probability of theta. This is your prior. It's a function from 0 to 1. It's peaked at 0.5, so you believe the coin is mostly unbiased. But you want to hedge your bets. You place some mass at the extremes, right? You observe one data set, which is a sample, which is one heads. Here's the likelihood function. If you just listen to your likelihood function, theta at MLE is 1. You multiply these two together and integrate out to get the constant. Here's what the posterior function looks like. Right? So in a sense, this is trivial because it's Bayes' rule, but this is the essence of learning. This is all of learning, right? We're born, we have some priors about the world, or we go into a new area and we believe something about the area. No, these people are idiots. And then they surprise you, and then it changes your model, but not quite. They're mostly still idiots. They may be doing fine, but it shifts your beliefs about which way things are going. Okay? And this doesn't stop here, right? Now this posterior serves as a new prior. You see another sample point, it changes your belief again. And this loop is essentially sort of all of learning. Does that make sense?